All right, so in our last video, we discussed conservation of energy. And conservation of energy meant that whatever amount of energy you started with was the amount of energy that you would end with. But then I went on to say that in a closed system, that wasn't always the case, that something outside of the system could add energy or take it away. Now that's not really truly conservation of energy. It's sort of an adjustment to it. And a better way to phrase that is with the Work-Energy Theorem. The Work-Energy Theorem relates that amount of work done to a system to the change in energy in the system. So let's look at it sort of from a fundamental or theoretical point of view. Basically what we were saying is you start with some amount of energy. If you add or do some sort of work on that system, you then end with a different amount of energy. If you solve this simple equation for work, you can see that work is the final energy minus the initial energy. Well, final minus initial, we've seen that before. That means change in. Really, work is the change in energy. We're either adding energy or taking it away. So, phrased like this, work is the change in energy in a system. And we're going to look at special cases. First, we can find work as the change in potential energy in a system if there's no change in kinetic energy. Now, this is most commonly going to arise where the kinetic energy is 0 at the beginning and 0 at the end. For instance, if there's an object sitting on the floor, say there's a box sitting on the floor. It's not moving. I pick it up and I put it on a table. I have done work on the box. I did not change its kinetic energy. It wasn't moving at the beginning, wasn't moving at the end. But I did change its energy. The change went into potential. It is now above the ground if I lifted it up onto the table. And the amount of work that I did on the box is equal to its change in potential energy. Alternatively, work might be the change in kinetic energy of something. But again, this is if there's no change in potential energy. Now, potential energy is really most commonly going to be gravitational potential energy. So, how do you change its gravitational potential energy? Well, you could change something's mass, but that's not likely. You're not going to change g, the acceleration of gravity. You're going to change its height. That is how you change potential energy. So, if something is on the same level, say a car driving on the road, or a ball rolling across a table or the floor, in either case, as long as you're not changing your height or position, if you're on the ground the whole time, your potential energy isn't changing. And so any work that is done on that object goes into a change in its kinetic energy. So for instance, if your car accelerates and you go from not moving to some velocity, well, the work done by your engine is equal to that change in your kinetic energy. Something gave your car energy. And we can find how much energy was given to it by looking at how its kinetic energy changed, how its energy of motion changed. And that works in the opposite direction too. I think there's a homework problem about catching a baseball. Well, that baseball is presumably at about the same height. It is probably going to drop a little bit, but a negligible amount. We're going to ignore that. As you catch that baseball, it's moving, then it stops. You changed its kinetic energy. It had kinetic energy, and then you took it away by catching it. The work done, the amount of work you had to do to catch that ball, is equal to that change in kinetic energy. So this is really where work should show up. If you have true conservation of energy, there's no external work adding or subtracting energy. That doesn't mean we won't have to make that correction. We will sometimes use that conservation of energy equation and have to account for some losses to friction. But if you only have one form of energy in a problem, if you're only concerned with potential energy or only concerned with kinetic energy, then you can quickly relate the work simply as the change in whichever type of energy is involved in the problem. Now, when you phrase it this way, you will get positives and negatives. And the way to interpret that is that the work done on something is positive if it adds energy, and it's negative if it takes energy away. Simply consider, kinetic energy real quick. This is final minus initial. Well, if I add energy to something, say it initially wasn't moving, so its velocity is 0, kinetic energy of 0, I then do work on it, I've given it energy. Its final energy is positive. Final minus initial is positive. I added energy to the object. And if that were the other way around, it would be negative. If something started with kinetic energy and then I stopped its motion, I took energy away. And its final energy would be 0 minus its initial energy, which would have been some positive number. I would get a negative value, and that represents me taking energy away. That's how you interpret your results when using the Work-Energy Theorem. All right, well, those are the basic ways in which we will set up problems, and I'll work plenty of examples with you guys in class illustrating how we approach problems, how we recognize, hey, is this conservation of energy or Work-Energy Theorem? I mean, really, they're very closely related, but there are subtle differences in how we approach problems if we're using one method or the other. So we'll end this video here, but stick around. I will have one more quick example illustrating just some of the basics of work, energy, and power. See you soon.